Before we begin, stop for a second. The next time you step onto a bus, close your eyes and just listen. You'll notice something curious. The roar of the engine isn't coming from the front. It's coming from the back. And if you look out the rear window, you'll see those cooling vents, those metal slats letting the engine heat escape. But why is it there? Why not in the front, like almost every car on the road? The answer isn't as obvious as you might think. What seems like a minor design choice actually hides decades of engineering, physics, ergonomics, and economics. Today, we're going to debunk the myth that engine placement is just a cosmetic detail, because it's actually one of the most critical design decisions in the manufacturing of mass transit vehicles. We're going to explore the history, the physics, the pros and cons, alternative setups, and some facts. Very few people know about bus engines. So, get comfortable, because this journey is going to be a long one, but a very interesting one. To understand why the engine is in the back, we first have to understand how we got here, and for that we need to travel back in time. The first buses of the 20th century were, essentially, trucks with a passenger body bolted on top. They were directly derived from cargo vehicles, and like every truck of that era, they had the engine in the front, tucked under a prominent hood. They were noisy, uncomfortable, and had a pretty problematic weight distribution. In the 1930s and 40s, manufacturers began to experiment. They realized that if a bus was going to carry people instead of freight, they had to completely rethink the design from scratch. The question was, what's the best way to maximize space for passengers? The answer arrived gradually. Companies like Mercedes-Benz, MAN, Volvo, and Scania in Europe, along with General Motors in the United States, began developing chassis specifically designed for buses. In these designs, the engine was moved to the rear or even mounted horizontally under the floor. This was a silent revolution that changed public transport forever. Fun fact: the first low-floor bus with a rear engine was introduced by Mercedes-Benz in Germany in 1954. It was called the 0321H, and it was a turning point in European transit design. In Latin America, the adoption of the rear engine was slower, and many countries continued using truck chassis for decades. However, starting in the 70s and 80s, rear-engine buses began to dominate long-distance routes and massive urban transit systems. Imagine a bus 40 feet long. With a front engine, the mechanical block takes up the first 5 feet of the vehicle. This forces the floor to be raised in that area, requires a transmission tunnel running down the center of the aisle, and eats up valuable passenger space right at the entrance. Now, imagine that same bus with nothing in the front. The driver sits directly over the front axle. The floor is completely flat starting from the front door, and all those recovered feet can be used for seats, a wider aisle, or even standing room for passengers during rush hour. This might not seem like a big deal until you run the numbers. A modern 60-foot articulated bus with a rear engine can carry up to 160 passengers. A front engine equivalent would barely reach 120. That difference of 40 people per trip, multiplied by hundreds of trips a day and thousands of buses in a city, is a monumental difference in public transit capacity. Fun fact: the longest articulated bus in the world in regular service is 82 feet long and operates in Switzerland. It's called the Autotram Extra Grand and can carry up to 256 passengers. Its engine naturally is located in the rear. Additionally, by having a flat floor, rear-engine buses allow for the installation of ramps or hydraulic systems for people in wheelchairs or with reduced mobility. In many countries, this isn't a luxury, it's a legal requirement, and the rear engine makes it technically possible without major complications. If you're enjoying this content so far, hit that like button right now. It helps us tremendously to keep bringing you videos like this. Thank you so much. Physics doesn't lie. A vehicle with weight balanced evenly between its axles is more stable, safer, and easier to control. When we're talking about buses, this is especially critical. In a front-engine bus, most of the mechanical weight is concentrated on the front axle. This creates a seesaw effect that is especially noticeable during cornering and sudden braking. The bus tends to dive forward and lift the rear, which reduces traction on the rear drive wheels exactly when you need it most. With the engine in the back, the weight is distributed much more uniformly. The rear wheels, which are generally the ones powering the vehicle, are right under the engine block. This means they have more weight pressing down on them, which translates directly into better grip on the asphalt. In adverse conditions like rain, snow, or poor roads, this difference can be life-saving. A rear-engine bus has significantly better traction on steep inclines and slippery surfaces. It's no coincidence that nearly all buses designed for mountainous regions or cold climates are rear-engine. Fun fact: during bus certification tests in Sweden, one of the most important criteria is performance on icy slopes. Rear-engine buses consistently outperform front-engine models, showing a traction advantage of up to 30%. Weight distribution also affects tire wear. An overloaded axle wears out tires much faster, increasing maintenance costs and safety risks. With a rear engine, wear is more even, which extends tire life and lowers operating costs. It might seem like a small detail, but engine noise has a massive impact on the passenger experience, especially on long hauls. It also affects the driver's concentration and well-being. A large displacement diesel engine like those found in motor coaches can generate noise levels between 85 and 100 decibels in its immediate vicinity. To give you some perspective, 85 decibels is like a blender running at full speed, and 100 decibels is like a jackhammer. When that engine is in the front, that noise is transmitted directly into the passenger cabin. With the engine in the back, however, you have feet of bodywork, acoustic insulation, and physical distance between the motor and the passengers. This can reduce noise by 20 to 30 decibels, practically the difference between shouting over a motor and holding a normal conversation. Fun fact: the World Health Organization states that prolonged exposure to over 70 decibels can cause hearing damage. Drivers of front-engine buses who work more than 8 hours a day have a significantly higher risk of developing long-term hearing issues in luxury long-distance coaches. Noise reduction is a major selling point. Some manufacturers like Neoplan or Cetra Add extra layers of acoustic insulation in the rear to drop noise levels even further, achieving under 60 decibels at cruising speed, similar to the interior of a high-end car. Vibration comfort is also improved. Engine vibrations, which in a front-engine bus travel directly through the chassis to the front seats, are considerably dampened when the engine is in the back. This is especially true for the middle section seats, which are usually the most popular with passengers. This gets a bit more technical, but it's fundamental to understanding why the rear engine isn't just more comfortable. It's more efficient. In a front-engine, rear-wheel drive bus, the power generated by the engine has to travel the entire length of the vehicle to reach the wheels. This is done through a long drive shaft, which can be 25 to 30 feet long on a large bus. That drive shaft has several articulation points called universal joints, which allow it to keep spinning even as the chassis flexes slightly during the drive. Each universal joint causes a small loss of energy due to friction. In a long drive shaft with multiple joints, those losses add up. Mechanical efficiency studies have shown that a long transmission system can lose between 5% and 10% of the engine's power before that energy even hits the wheels. With a rear engine, the distance between the engine and the wheels is minimal. The transmission is short, direct, and has very few friction points. This doesn't just reduce energy loss. It also simplifies the mechanics, making it less prone to failure and easier to maintain. Fun fact: a long-distance bus covers approximately 125,000 miles a year, with a 7% efficiency improvement in the transmission system. That same bus saves the equivalent of thousands of gallons of fuel annually. Multiplied across an entire fleet, the savings are staggering. Furthermore, because the transmission is shorter and simpler, maintenance intervals are longer and repair costs are lower. Universal joints are wear items that need periodic replacement. The fewer you have, the lower your long-term maintenance bill. Think about the difference between driving a truck with a long hood and driving a delivery van. The forward visibility is radically different. A truck driver with a hood has a massive blind spot right in front of the vehicle, making precise maneuvers in tight spaces difficult. Front-engine buses face a similar problem. Even if the engine is under the floor or behind a cover, it still occupies space in the front that could be used to improve visibility. In modern models, some manufacturers have even had to add front-facing cameras to compensate for this blind spot. With a rear engine, the driver has a completely unobstructed forward view. Modern rear-engine bus windshields can be massive, almost panoramic, which greatly improves situational awareness, especially at complex intersections, busy bus stops, or pedestrian zones. This better visibility also improves active safety. Accident studies in public transit show that good forward visibility reduces accidents by a significant percentage, particularly pedestrian strikes, which are the most serious type of urban transit accident. Fun fact: European bus certification regulations require the driver to be able to see the ground less than 7 feet from the front of the vehicle. This rule was designed specifically to protect pedestrians and cyclists, and it's much easier to meet with a rear-engine design. Subscribe to the channel. If you haven't already, hitting the subscribe button and the bell icon ensures you won't miss any of our upcoming videos. We look forward to seeing you in the community. It would be dishonest to only talk about the advantages. The rear engine isn't perfect, and there are very specific reasons why not every bus in the world has adopted this setup. The most famous challenge is the rear overhang or tail swing effect. On a large bus, the back of the vehicle extends considerably past the rear axle. When the driver makes a sharp turn, the tail of the bus swings outward with an arc that can catch inexperienced drivers off guard. This isn't a theoretical problem. It's the cause of numerous incidents in cities where drivers haven't been properly trained to manage this behavior. The rear overhang can reach up to 10 feet on the largest buses, meaning that when turning a corner, the back end can swing into the opposite lane or hit street furniture. Another major downside is maintenance access. Rear engines are usually tucked into a relatively tight compartment, which can make inspection and repair tasks difficult. In front-engine buses, a mechanic has easy access by just popping a hood or a side cover. In a rear-engine setup, you often have to open rear panels, work in awkward positions, or even access parts from underneath the vehicle. Fun fact: bus mechanics in large metropolitan depots estimate that routine maintenance on a rear engine takes 15% to 25% more time than the same tasks on a conventional front-engine design. However, the higher reliability of the rear engine means those service calls are less frequent. There is also the issue of cooling. A rear engine generates heat that must be dissipated, but because it's at the back, it doesn't get the natural airflow. A front engine receives while moving. Rear engine cooling systems are more complex and expensive, requiring multiple radiators, electric fans, and in some cases, extra heat exchangers. In extremely hot climates, this thermal challenge can be a deal breaker. In cities like Dubai, where summer temperatures can exceed 115 degrees Fahrenheit, rear-engine buses require specially reinforced cooling systems that add weight, cost, and complexity to the vehicle. If the rear engine has so many advantages, why are front-engine buses still being made? The answer is multidimensional. First is the cost. Front-engine buses derived from truck chassis are significantly cheaper to build. By sharing platforms, components, and assembly lines with cargo trucks, manufacturers can spread development costs over a much higher production volume. A typical North American school bus with its unmistakable long nose can cost 30% to 40% less than an equivalent rear-engine bus. For developing countries with tight transit budgets, this price gap is the deciding factor. In many cities across Africa, Asia, and Latin America, front-engine buses remain the most economically viable option, despite their technical drawbacks. The second reason is ease of maintenance in environments with limited infrastructure. In rural areas or countries where specialized shop networks are scarce, a conventional truck engine can be repaired with basic tools and general mechanical knowledge. A modern rear-engine bus, with its complex electronics and auxiliary systems, might require specialized diagnostic gear that simply isn't available in many parts of the world. Fun fact: in countries like India and Brazil, and several African nations, over 60% of buses in service still use truck-derived front-engine chassis for these exact economic and maintenance reasons. The third reason is specific use cases. North American school buses, for example, have a very deliberate front-engine design. In the event of a head-on collision, the engine acts as a massive crumple zone, protecting the passengers. Additionally, the rear emergency door occupies the space where an engine would go in other designs. For this specific job, the front engine offers safety advantages that outweigh the ergonomic downsides. There is a third configuration that deserves its own attention: the mid-engine. While it's less known to the general public, it's actually a fascinating solution that tries to combine the best of both worlds. In mid-engine buses, the motor is placed horizontally, directly under the floor in the middle of the vehicle. This setup might look like a compromise, but it has very specific benefits. Weight distribution is the most balanced of any configuration. With the engine exactly in the center, weight is split almost perfectly between the front and rear axles. This leads to the best possible stability in corners, under braking, and during high-speed maneuvers. Articulated buses, the ones with an extra section joined by a flexible bellows, benefit especially from mid-engines. By placing the engine near the articulation point, both the front and rear sections can contribute to the vehicle's momentum, improving traction and maneuverability. Fun fact: the Vios Mercedes-Benz Citaro G articulated bus, one of the most widely used in European public transport, can be equipped with either a mid-engine under the floor or a rear engine depending on the variant. Cities with lots of hills usually prefer the rear-engine version for better climbing traction. However, the mid-engine has its own limitations. The main one is maintenance access. An engine mounted horizontally under the floor is extremely difficult to reach for repairs. Technicians have to lift the vehicle, remove floor panels, and work in very cramped positions. This drives up maintenance time and costs. Another limitation is that a mid-engine takes up underfloor space that could be used for storage. On long-distance coaches, the luggage bay is essential. With a mid-engine, that space is partially occupied by machinery, reducing cargo capacity. All this talk about engine placement might seem irrelevant in the context of electric transit. And to some extent, that's true. Electric buses are radically changing the rules of the game. In an electric bus, there is no central thermal engine generating heat, noise, and vibrations that needs a specific home. Instead, there are electric traction motors that can be placed directly in the wheels, known as hub motors. This completely frees up the interior space for passengers, batteries, or auxiliary systems. The batteries, which are the heaviest part of an electric bus, can be distributed across the entire chassis, optimizing the center of gravity in a way that would be impossible with an internal combustion engine. Fun fact: the BYD Cane electric bus, one of the world's best sellers, can reach a range of nearly 190 miles on a single charge. Its electric motors are integrated directly into the rear wheel axles, eliminating the need for a central engine or a conventional transmission system. However, the transition to electric buses won't happen overnight. Globally, over 95% of buses in service still run on diesel or gas. Replacing that fleet will take decades, and during that time, the discussion about engine placement will remain very relevant. Furthermore, in parts of the world far from power grids, or in countries where the electrical infrastructure isn't reliable enough, thermal engine buses will remain the only viable option for years to come. In those contexts, understanding the advantages of the rear engine is still absolutely pertinent. And so, we've reached the end of this journey through one of the most fascinating and overlooked topics in transport engineering. We've seen that where an engine sits in a bus isn't an arbitrary choice. It's the result of decades of technological evolution, millions of miles of testing, and a delicate balance between efficiency, safety, comfort, and economics. The rear engine, with all its benefits in space, traction, noise, mechanical efficiency, and visibility, has become the gold standard for most modern high-capacity buses. But as we've seen, it's not a universal fix, and there are still contexts where front or mid-engine setups offer advantages that can't be ignored. What I find most fascinating is that every time you ride a bus, you're unknowingly benefiting from an engineering solution refined over generation. Every seat you take, every turn the driver navigates smoothly, every quiet trip that lets you read or listen to music without engine roar. Those are the results of technical decisions that started being made over 80 years ago. The next time you board a bus, take a second to think about all of this. Notice where the engine is. Listen to the relative silence of the cabin. Appreciate the width of the aisle and how easy it was to get on. And remember that behind that design, which seems so obvious, there are decades of engineering applied to one simple goal: moving people efficiently, safely, and comfortably. Because in the end, that's what good engineering does. It solves problems so elegantly that the solution feels natural, leaving almost no one to wonder how it even came to be. Until the next video.